Assalamualaikum. Hello, everyone. First of all, I would like to welcome you in this first keynote speech. Thank you for joining us. Let me introduce myself. I'm Feri Wijayanto, and it is an honor to me to become a moderator of this speech session. So, yeah, since I believe we hold this conference online, so I believe there are some differences in the time zone. However, I hope it does not lower your enthusiasm to follow this conference agenda. So since you may know that we have 6 keynote speeches, so I hope you will not miss them. And now, yeah, this session is our first keynote speech. Will be delivered by Dr. Kun Zhang. Hello, Dr. Zhang. Can you hear me?
Hello, Feri. Yes, can you hear me?
Okay. How are you?
Good, thank you. How are you?
I'm good. Thank you.
Nice,
so
nice to meet you.
Nice to meet you too. So yeah, thank you for joining us today and share with us with your expertise.
My pleasure.
Yeah. How's the weather in Pittsburgh now?
Oh yeah. Since in United States, things are not very good, but in Pittsburgh it's fine.
Okay. Yeah. Okay. Yeah. So yeah, before we begin, let me first introduce Dr. Yang a bit. So yeah, Dr. Kun Zhang is an associate professor of philosophy and an affiliate faculty in the machine learning department of Carnegie Mellon University, and a senior research scientist at Max Planck Institute for Intelligent Systems in Germany, and is interested in the connection between causality and machine intelligence, and has been actively developing methods for automated causal discovery from various kinds of data and investigating machine learning problems, including transfer learning, adversarial vulnerability, and deep learning from a causal view. And he also his work has been widely published in major artificial intelligence and machine learning venues. And also Dr. Zhang co-authored a best student paper for UAI and best finalist paper for CVPR, and received the best benchmark award of the Causality Potluck Challenge. He also been frequently serving as a senior area chair, and senior program committee member for most major conferences in machine learning or artificial intelligence, including NeurIPS, ICML, UAI, IJCAI, and ICITDA. So in summary, he is really an expert in the machine learning, especially in causality research area. So I hope you can enjoy and gain some knowledge during his speech. So in this session, we will have time around 70 minutes. So probably we will try to split the time around 50 minutes for the speech and 20 minutes for question and answer sessions. How do you think? What do you think, Dr. Zhang? Is it 50 minutes enough for you?
Perfect.
Okay.
Yeah.
Okay.
50 or 54, something like that. Yeah.
Oh yeah. Yeah. Okay. So and later in the question and answer session, you can ask directly to Dr. Zhang or using chat room. Yeah, but yeah, it will prioritize the one who want to ask directly. So yeah, I would not hold any longer. So let's just start this our first keynote speech. So Dr. Yang, are you ready?
Yes. Let me share my screen.
Okay.
Great. Yeah. Thanks a lot.
Yeah.
It's very nice to see the wonderful, beautiful video. It's really vivid and so beautiful. Yeah. And thank you very much, Feri, for the nice introduction and the chairing the session. And also thanks to Rita for the invitation. So we are friends. We have been friends for years. Okay, great. Thanks a lot for coming. Good morning or good afternoon. But for most of you, it's good morning, right? I hope you enjoyed the talk. So essentially, in this talk, you can see how we can learn causal representations and making use of them. So here by causal representations, I mean the causal picture underlying the data. So in many cases, we talk about the causality. We say X causes Y, right? So essentially, there's an arrow from X to Y. It's X causes Y. And in many cases, we have to go to the hidden world because what we see might be just reflections of the underlying causally interacting variables, right? Like we see image pixels, but image pixels do not cause each other. Instead, they were generated by the high-level concepts which may cause each other. So in this case, we have to recover the hidden world with the hidden variables and their causal relations. And then, of course, if you care about the causality, for instance, if you care about interventions, you have to make use of causal relations. Otherwise, even if you just want to do machine learning, you can see that, oh, for many tasks, we really have to go to the level of causality or some similar level. Okay, so you'll see how we can do this in this presentation. Okay, let me start with some very general phenomena in machine learning. So right here, you can see on the left, we have a picture. It's panda, right? If you add some noise to this specific noise to this picture, or if you just change a particular pixel, then in some way, the machine will say, oh, it's something different. It's not a panda anymore. This is very strange, right? Because for human beings, clearly it's the same picture, but the machines will say, no, it's not. This is known as adversarial attack. So, and this is one of the most fundamental problems with deep learning systems. At the non-parametric system, we cannot really guarantee the performance if the distribution does not satisfy some specific property. What can we do in this case? So roughly speaking, first of all, why do we have this phenomenon? Essentially, as long as the machine's decision process and our decision process are different in some way, then you can always tune the input, right? Change the input in a specific way so that either machine decision become different or our decision become different. And as a consequence, you can always have this adversarial attack problem. In other words, in order to solve the problem, we have to enable the machine to think in a similar way. In other words, we should give the machine the ability to represent knowledge in our way, right? So how can we represent knowledge? We use generative view. We see different things. We want to find a model, generative model to explain different phenomena, different scenarios and different tasks, right? So how can we give the machine this ability? That's the essential problem in artificial intelligence. In particular, if you want to achieve general purpose artificial intelligence, you have to do so. And then let me say a few words about artificial intelligence. So usually in traditional machine learning, we assume that the training data and test data have the same distribution. As a consequence, we learn something from training data and apply the learning machine to the test data. And we are happy because the performance is guaranteed. And this is just because we always have the same distribution. However, in reality, most of the time, this is not the case. For instance, here, we human beings have a lot of capacity that machines at this moment, machines do not have. For instance, if you play badminton very well, right? You can quickly learn to play ping pong, and you can play ping pong very well. Why? Because you know automatically how to decompose the complex task into small, simpler ones, and you know how to transfer the skills, right? And right here, you can see as a human driver, even if this is a new scenario, you can see the essential property of the scenario. You can draw the connection between this scenario and previous ones, and you can make the right decision. But for machines, this is almost impossible. So basically, we see the phenomena. To summarize, if the machine to be intelligent, then the machine should have some ability to understand what's going on. I'm not giving a definition of understanding, but later you can see we'll make this clearer. Because of this understanding, the machine is able to do control or intervention to achieve some goal. And the machine will automatically decompose complex things into simpler things. And in the other direction, the machine could also integrate information from different aspects so that the machine can have a big picture about the whole scenario. The machine can learn with few examples by leveraging the experience, right? Something the machine already learned in the past. And machine can do not only the interpolation, but also extrapolation. Even if we are faced with a new scenario, we know how to solve the problem. So you just saw a lot of phenomena associated with intelligence. Study how the brain works, and then I can just build something to fully mimic how the brain works. That's a machine learning way of doing intelligence, right? You are giving training data, you want to do something specifically for the training data. However, if you want to achieve some general purpose intelligence, that's not really a feasible way, because you have to be adaptive. You have to adapt to new material, right? New tasks and so on. Then how can we define intelligence? So basically, a fundamental way is to view intelligence from the evolution and selection perspective. We define intelligence for two reasons. Basically, we survive and we prosper. First of all, we survive in almost all scenarios. That means, we make good prediction and decision across all possible scenarios, right? From the statistical perspective, in order to do so, we have to make use of some inner compact representation of the external world, so that we can make use of different kind of knowledge, right, to solve a specific problem in light of the connections between different scenarios. In other words, we want to use this inner compact representation. At the same time, we are different from other type of animals. We are creative. We are more creative. We discover and make use of the causal representation underlying the problems. Because of this ability, we can make changes. We can change the world so that some expected thing will happen. Now you can see we have two kinds of representations. Essentially, they are consistent. When we were very young, we couldn't really do interventions. We couldn't really verify this is causal. However, we still learn the representation of the world, right? And later, we were able to do interventions to verify a lot of causal claims. There does not seem to be a huge gap between the two types of representations. And now you can see, in light of this connection, we have a couple of questions to answer. First, from data, by analyzing data, we can find a representation. Under what assumptions can we be sure that the learned representation is causal? So this is causal discovery. Second, if we know something about the causality, how can I make use of a causal knowledge to improve our prediction performance across different scenarios, right? And third, if you just want to make adaptive prediction, or if you want to do transfer learning in an arbitrary new scenario, is it necessary to always use the causal information? Maybe something about the inner compact representation would be enough, right? So basically, you can see fundamentally there are two problems. One is how to learn causal model, causal representation. The other is how to make use of some kind of representation to improve our prediction performance across different scenarios. Okay, so in this talk, I will start with how to learn causal representations. And first, I will introduce the traditional methods, including constraint-based method or conditional independence-based method, and functional causal model-based method. You can see how they work. You can see the basic procedure. And then I will say a few words about a particular way to learn a hidden world, hidden causal representation, underlying what we see. And then I will say something about the causal discovery from non-stationary or heterogeneous data. This is important because we use this method to learn the representation for transfer learning. So after that, I'll introduce some method for transfer learning based on the learned representations. And you can see it's really essential to learn and make use of some kind of representations for complex learning tasks. If you have questions, please, yeah, you may just let me know. Let me give an example. So right here, this is a data set collected by my collaborator, Molly Novak. Her last name is very cool, right? Novak, just go forward, Novak. So she collected 250 skeletons all over the world, and she measured 8 variables. In archaeology, they really want to see the causal relations between those variables, including sex, location, geometric location, climate, cranial shape differentiation right here, cranial size right here, regarding how big this part is, and so on, and diet, and so on. Because in archaeology, people really want to see why people from different areas look different. And given this understanding, they want to make a prediction into the future, right? Suppose we know that the environment will change in a specific way. How can we predict what the future people, right, look like? And so on. So you can see for these kind of problems, you cannot really do interventions. Even if you can really do interventions, you can force people to move, right? You have to wait a long time. After the evolution process, you can see something, but it's definitely very long. You cannot wait. So now you can see in reality, very oftentimes, we cannot discover causal relations by doing interventions, by changing the system in a specific way to verify causal claims. We have to analyze the data. In fact, it's really nice that by analyzing data, we can discover very detailed causal information. I will show the solution to this example later. Essentially, if you want to discover causal information from data, the first important problem is to see the connection between the underlying causal structure and the property of the data, right? So what property do we have? When we say it's a causal system, basically we mean the following thing. It's another level of independence. When we say X causes Y without a common cause, we mean that, basically for X, Y, we actually have 2 processes. One process generates X, the cause, the other process generates the effect Y from X. Although X and Y are dependent, the 2 processes are not related. It's just rain, right? Rain and wet ground. We have a process to generate rain. We have another process, separate process, to generate wet ground from rain. The 2 processes do not share information. They are separated. That means, the generating process for the cause and the generating process from the cause to the effect are completely irrelevant to each other. This is another level of independence known as process independence. And we can have different ways to instantiate this process independence in statistical ways. First one is to make use of conditional independence between the observed or measured variables. Essentially, now I'm going to show how the PC algorithm, this is PC algorithm, as a typical constraint-based method, or by constraint, I mean conditional independence constraint-based method for causal discovery. So P is for Peter Spertis, and C is for Clark Glimmer. They are just my senior colleagues at Carnegie Mellon. So PC are just the first letters of their first names. This is how it works. Given data, from data, we can discover a set of independence and conditional independence constraints. Then we want to find a graph to satisfy those constraints, or a set of graphs to satisfy the constraints. And then you can see if they are independent, then we are sure that there are no causal link between them. Otherwise, they cannot be independent, conditional independent, because this path is not, it cannot be blocked by any variable. As a consequence, if you see the independence between 1 and 3, you know, they are not adjacent. 1, 4, not adjacent. 3, 4, not adjacent. Now we have a skeleton. And then right here in this example, you can see 1 and 3 are independent. Then this is the only way to derive the causal directions. Otherwise, if you change the direction either this way or this way, you can see X3 and X1 will share information. Generally speaking, they will not be independent. So we have we have to consider x2 as a common effect of x1 and x3. This is not the case. Right here, we cannot orient the direction this way from 4 to 2 because x1 and x4 are not independent. And then you go further, that means we have to orient this guy this way. Because otherwise, if this guy goes in the reverse direction, we are going to have a fake V structure, fake common effect. So this way, now we can see, oh, we can discover information of the underlying causal structure from data. Specifically with the condition independent based method, we end up with a Markov equivalence class. Usually, it's not a single directed acyclic graph. It's a set of graphs. All of them share the same skeleton and the same V structure. By V structure, I mean this kind of structure. Two variables, not adjacent. They are adjacent to a common variable, and they are causes of that common variable. This is V structure. Okay, now let me show the example, show the results on the data I just showed. Right here, we use the PC algorithm combined with our kernel-based conditional independent test. You can see if you want to make use of this method, you have to infer independence and conditional independent relations from data, right? This is the result. You can see a lot of edges are directed, as you can see from here. This means our gender and climate are independent, and they are causes of cranial size. And this relationship has been well discussed in the literature. Generally speaking, so for people from North Europe, the cranial size is pretty big. Why? Because it's very cold, right? They need to warm the air before really inhaling the air. That's why this part is bigger. And you can see for some links, right here, some links are not directed. However, in many cases, we can introduce some background information. For instance, here, this is location, this is climate. We believe climate causes we believe location causes the climate. As a consequence, we have this direction. If you have this direction, you can do orientation propagation. If this guy goes this way, this guy must go this way. Otherwise, you are going to have a fake V structure, and so on. So now we have a direct acyclic graph. Many relations have been discussed in the literature, and more importantly, you can see here, we can see the causal influence from diet to cranial shape differentiation. Basically, it means what you eat, diet, will influence your looks. This is the cranial shape differentiation, essentially the shape right here. It's nice, so we should be careful when we eat. But now, by analyzing data, we see something more detailed. In the literature, they always claim that yes, diet influences cranial shape differentiation. Now, from this picture, we know diet influences that in an indirect way. This causal influence takes place via another two variables. One is the level of attrition in teeth, the other is some behavior. So we can easily distinguish between direct and indirect causal influences. Everything is very simple. We just analyze data. Data will not lie. Data will not lie. If data lie, basically it's just because you didn't really see through the data, right? There might be noise in the data. You have to consider that. Okay, so this is the first example. Now, some of you may wonder, oh, right here, in this matter, it seems that you do not consider possible confounders. By confounder, I mean unmeasured common cause of two variables in the system, right? Confounder is a really big issue because if you do not properly consider confounder, you are going to have extra or spurious causal relations. In fact, even with the conditional independent relations, we can say a lot of things about confounders. Let me just give two examples. So suppose we know the four variables are independent this way. Okay, we have this picture. One, two not adjacent, they are independent. 1, 4 not adjacent, 2, 4 not adjacent. And I already worked out this example. We know this is a V structure. This guy goes this way. Good. Now the question is, do you think it's possible to have a confounder behind X3 and X4? Do you think this is possible at all? The answer is no, because if you have this confounder right here, then conditional X3, this part will be open. In other words, generally speaking, X1 and X4 will not be conditionally independent given X3. Okay, so since you observe the independence between 1 and 4, given 3, this is not possible. Now you can see it's very cool. By analyzing very few variables, you can really say something about the whole universe. You know that, oh, I don't care. If I observe this set of independent relations with enough data, then I can just say x3 and x4 do not have a confounder, unmeasured common cause. And furthermore, I can say that x3 must be a direct cause of x4. It's very strong. And here you can see some examples. So suppose x1 is raining, x2 wet ground, x4 is right here slippery. So you can see x3 1 and x4 are independent given x3. You know that x3 is not a cause of x1. Then you can immediately draw the conclusion that, oh, x3 must cause x4 without the confounder. So this kind of method can be used in the studies of history, philosophy, and social sciences. Essentially can really verify a lot of causal claims. Okay, let me give another example. We have 4 variables again. We observe this set of independent relations, and then because they are independent, they are not adjacent. Now you can see something interesting. So 1, 2, 1, 4 independent, 1, 3 independent, 1, 4 independent, 2, 3 independent. Since 1 and 4 independent, if you believe there are no confounder, then you would have a bit structure here, right? Since 1 and 4 independent, they cause x2 together. And similarly, since 1 and 3 are independent, you have the same thing. Now you can see, oh, what can I do here? Contradiction. Why do we have this contradiction? It's just because there should be confounder. Without the confounder, you cannot explain this statistical pattern in the data. So right here, there must be some confounder. And in this case, we are sure that there are some confounders underlying some variables. Let me give an example. That's one binary variable to indicate whether I'm not sick. X2 is whether I'm in this lecture room. Suppose we are currently in the lecture room. And X4 be you are also in this lecture room. And X3, whether you are sick. Now you can see 1 and 4 independent, 1, 3 independent, and so on. We can see this set of independent relations. At the same time, clearly, you know, X2 and X4 are not independent. Both of us are in the lecture room right now, right? But now, in light of this analysis, we know although both of us are in the lecture room, X2 and X4 are dependent. There is no direct causal influence between them, right? You are here not because I'm here. I'm here not because you're here. It's because there's a common cause. We have this event, right? So we can really infer the existence of common cause, hidden common causes. Okay, so this idea was used in the algorithm called FCI, fast causal inference. Essentially, even with the conditional independence, we can say something about confounders, about unmeasured common causes. In the last 15 years, new methods were developed based on functional causal models. Essentially, we make use of independent noise condition. This is a linear non-Gaussian model. The effect is a linear function of the cause plus some independent error, independent noise term. As you can see from this illustration, in this case, something interesting will happen. X causes Y, X causes Y. So X and the noise are not Gaussian. Then if you regress Y on X, you can see the noise term would be independent from X because you just recover the underlying true causal model. If you regress X on Y, which is the anti-causal direction, you can see although the regression residual is uncorrelated from Y, they are not independent. As a consequence, you can see the asymmetry between two variables. More generally, we have different kinds of nonlinear functions. Let me say a few words about the very general model. So we developed this model called post-nonlinear model in 2005 because we started with a linear model and a nonlinear additive noise model, nonlinear function with additive noise. And we found that in many cases, we cannot really explain the cause-effect relationship. We believe that the causal model should be very general so that it can finally approximate the true causal process. At the same time, we have to guarantee the identifiable causal direction, meaning that wrong causal direction will not satisfy some property of the model. In particular, By that, I mean the property of independent noise. For the right causal model, we assume the noise is independent from the cause. Okay, so what model should we use? We believe that at least three factors should be considered. The cause may have a nonlinear effect. We have noise, we have a sensor measurement distortion right here. If you put them together, we have the post-nonlinear causal model. The effect is a nonlinear distorted version of the nonlinear effect of cause plus noise. Now you can see this function is functional form is very general, right? If this is linear, this is linear, it's a linear model. If this is linear, then it's nonlinear function and with additive noise. In fact, even if the noise is multiplicative, as you can see from here, or as you can see from here, from this scatter plot, is multiplicative. It's actually also a special case of this model. You have exponential transformation here, log, and they are independent. So this is new noise term, right? So now you can see, oh, this is the very general form. And with this form, we can really distinguish between cause and effect. Here you can see some empirical results. We are given data pairs. We are given a data set for two variables, x1 and x2. We can see a lot of data points. First, we assume x1 causes x2. We fit this model. We automatically learn the nonlinear functions and the noise term, right? Just like a regression. Once you find a functional function for regression, you have the noise term. If you assume x1 causes x2, the ultimate noise is independent from x1. For the reverse direction, where you assume x2 causes x1, you can see the ultimate noise cannot be independent from x2, the hypothetical cause. Okay, and we can conclude that according to this model, x1 causes x2. Actually, x1 is the altitude of 300 cities, and x2 is the temperature. Altitude causes temperature, not the other way around, right? Here you can see another example. So similarly, if you assume x1 causes x2, right? You fit the model, you learn nonlinear functions, and you estimate the noise. Now you can see, oh, the noise is independent from x1. But if you assume x2 causes x1, then the noise term cannot be independent from the hypothetical cause. We say that, oh, according to this model, x1 causes x2. We can really distinguish between cause and effect. Actually, here x1 is age, x2 is wage per hour for more than 10,000 people, right? So age causes the wage per hour, not the other around. And here you can see the learned nonlinear functions. Basically, a lot of data, this model just gave the right causal direction, correct causal direction. With this, we just got the best benchmark award in the challenge. This changed a lot of people's mind. Now you can see without making use of temporal information, no time information, you can really see the causal direction between the two variables from their data. I want to note that so far, I haven't talked about the temporal information. We are not dealing with time series because usually it's simpler to dealing with time series. If you can discover causal information from ID data, then if you are given time series, you can just further incorporate the temporal constraint that cause cannot, effect cannot happen before the cause, right? So the fundamental case is the ID case. Without the time information, how can we discover cause-effect relationship? Yeah, you just saw some empirical results. Now you can see some theoretical guarantee. Essentially here, we show that in only very few situations, cause and effect are symmetric in the sense that both directions admit independent noise. How can we achieve this? Basically, suppose x1 causes x2, then we have the distribution generated by this causal model. Then suppose the same distribution can also be explained by the reverse direction. Then we can find a condition. If the condition is very restrictive, then we know, generally speaking, only one direction can be used to explain the data. So right here, yeah, given the data assumption, we have a set of equations, solve the equation, and then we have the 5 situations in which cause and effect are symmetric, in the sense that the reverse direction can also find an independent noise term. Apart from those 5 situations, that's not possible. The first case, the linear Gaussian case. It's clear in the linear Gaussian case, causal information disappears if you have only 2 variables. And you can just understand this from the perspective of central limit theorem. We know central limit theorem, right? It said that if you have the sum of independent variables under some conditions, as the number of independent variables go to infinity, the sum will convert it to a Gaussian distribution, right? And at the same time, we have a Kramer decomposition theorem that says if you have a sum of a finite number of independent variables, and if the sum is Gaussian, then every variable right there is Gaussian. So that means basically Gaussian variables are in a closed system. If anything non-Gaussian and interacts with those Gaussian variables, everything will be non-Gaussian. Okay, now you can see before you reach the equilibrium state of Gaussian distribution, right, it's non-Gaussian. You still have the process information. By process information, I mean causal information. However, if the data distribution is really Gaussian, then the process already converges. If it converges, then we do not have the process information at all. We have a single point. That's why the causal information disappears in the Gaussian case. So basically, all those 5 situations are very specific. You have to tune the nonlinear functions and the distributions very carefully so that one of them holds true. In other words, we can say, generally speaking, the causal direction is identifiable, even if data were generated according to this very general form, very general function. By identifiable, I mean only one direction admits, only one direction satisfies our assumptions, our assumption of independent noise. And since this model contains linear model and the nonlinear additive model that special cases, we know, or the result will also hold true for those models. So generally speaking, we know cause and effect are not symmetric in the distribution. We can infer which variable is the cause and which variable is the effect. In practice, there are so many practical issues to consider. Why? It's because we have to deal with measured data. The data were generated by not only the causal process of interest, but also how you measure the data, right? So here you can see a long list of practical issues. And right here, you can see those papers de-highlighted in gray were published by our group. So first of all, we have to deal with all kinds of linearities, and we have to deal with not only continuous variables, but also continuous variables and even mixed continuous and categorical variables. We have to deal with measurement errors, right? If you use a tool or instrument to measure something, usually you will have error. And in many cases, we can only use a surrogate to measure some variable, say safety of the in a particular region. How can you do that? Maybe you can just use the number of crimes per month, right? It's a surrogate. It's not really identical to the underlying true variable, although they are similar. You have measurement error. We have selection bias. Whenever you work with internet data or work with data collected in hospital, you have measurement error because where the data point is included depends on the value of some of the features. We have confounders. It's possible to have confounder everywhere. So we have to go to discovery in the presence of confounders. And more specifically, in some cases, we care about the confounder. We care about the relation between confounders. So we have to go to the level of latent causal representation, for which I will say something in half a minute. If you work in healthcare, there are so many missing values. You have to deal with missing values. And if you have time series, you can further leverage the information of time information to improve the result because they're time series. And in many cases, we have non-stationary or heterogeneous data. Distribution is not fixed. We can also leverage the features of such data to improve the causal discovery results. So first, let me say something about hidden causal representation learning. So here you can see the problem definition. We have data right here on the left. We've measured x1, x2, x3 to x8. So we measure xi variables. And it's possible that those variables might not directly influence each other. Instead, they were generated by hidden variables, L1, L2, L3, and L4. Those hidden variables are causally related to each other, right? So we can have different pixels right here. We can have different concepts underlying the image pixels. They are causally related. How can we recover those underlying variables and their relations. So this is hidden causal representative learning. You can even allow causal interactions between the observed variable, doesn't matter. Basically, we want to go to the level of hidden variables. We want to discover their relations right here. Okay. So I will say something about our recent paper accepted to New York this year. So let me say a few words about the independent noise condition. With this condition, we can easily discover causal information in the situation without the confounders. So right here, we say Z, a set of variables, and Y, single variable, follow the independent noise condition if the regression residual of regression Y on Z is independent from Z. So it's just a regression error, right? If the regression residual is independent from Z, we say, oh, independent noise condition holds true. And then this is the case if and only if two conditions hold true. The first one is that, oh, Y is not the cause of any variable in Z. If this guy goes this way, then it's not possible to have this condition. Second, Y and any variable in Z cannot be confounded. There are no common cause right here. So that means, oh, by verifying this condition, I can find the causal orders. As you can see from here, we know, oh, 2 causes 3, we know causal order, 2 causes 1, and 2 causes 4. So 2 is the first variable, is the root variable in the causal order. And then you can find the second one, and so on. If you know the causal order, then you can just do regression with the sparsity constraints on the coefficients. You can find the whole causal structure. This is independent noise condition. Here we assume there are no latent confounder. In reality, we can have latent confounders. So this is the motivation which I just explained. In many cases, the measured variables do not directly cause each other. For instance, in psychometric questionnaires, the answer scores do not cause each other. Instead, there were reflections of the underlying hidden states, mental states, right? And we want to infer the mental states and the relations between different mental states, the hidden variables. What can we do? So here we propose a linear non-Gaussian latent variable model, as you can see from here. We observe those variables. We want to go to the level of the latent variables and infer causal relations. Actually, the whole model is identifiable based on a so-called generalized independent noise condition, for which I will just give a rough picture. So Z is a set of variables, Y is a set of variables. Basically, they are just two disjoint subsets of the observed variables. We say ZY satisfies the generalized independent noise condition if and only if there exists a non-zero linear combination of the variables in Y that is independent from Z. So this looks like an independent noise condition, right? Or some linear combination is independent from Z. But here it's not, we're not doing regression. That's why it's not regression residual. Instead, we have a linear combination of the variables in Y. It's interesting to see the graphical implication of this condition. Essentially, this condition, if this condition holds true, then we can say Y, this set of variable, and that set Z, that set of variable, are deseparated by the latent common causes of Y. This will immediately give us information about where the latent variables are and the causal relations between the latent variables. For instance, here, if you consider x4 and x6 as Y, and x1 and 3 and 2, right? Those three variables as Z. Now you can see this condition holds true. Y is as Y, so this is Y, this is Z. This holds true. Why? Graphically speaking, this is because the latent common causes of Y, L1 and L2, deseparate Z from Y, right? And in contrast, you can see if Z is x4 and x5 again, but Y variable set is 1, 2, and 5, then this condition does not hold true because the common cause of Y, latent common cause of Y variables right here would still be L1, L2, but L1 and L2 do not decelerate X6 from X5. As a consequence, this condition, the generalized independent condition, will be violated. In other words, by checking this condition, you can really see where the latent variables are and the causal ordering of the latent variables. As a consequence, we can estimate the whole model. So right here, we can solve the problem in 2 steps. First, we can find the causal clusters. So variables sharing the same latent variables as parents are in the same cluster. In this example, we have 3 clusters. And second, we can determine the causal order of the latent variables by checking the condition. And then if needed, you can just estimate all those linear coefficients. And finally, you estimate everything right here in this picture, causal picture involving latent variables and their causal relations. Here you can see application. This is a teacher's burnout dataset. And right here, we have a lot of 28 variables. We find the clusters, and this is a hypothesized model by experts that discover the clusters are the same as the hypothesized model by experts that derived this model based on their understanding of the process. But now, by analyzing only the 28 variables, we discover the same clusters, and also we discover the same causal relations, the same causal orders of the latent variables. Essentially, we can really recover the underlying truth from the observed variables or measured variables. Okay, now let me spend 2 minutes on the last problem regarding causal discovery. In many cases, we have non-stationary data. If you measure data over time, as time goes on, the distribution can change. If you measure data under different conditions or in different locations, the distribution may be different. Why is the data non-stationary? Generally speaking, this is because we have some variable in the background. We do not measure the value of this background variable, and its value may change either over time or across domains, across datasets, right? As a consequence, we can see the change in the distribution. And then from the statistical perspective, non-stationary data is really horrible because you don't have a fixed model. But from a causal perspective, we really like non-stationarity. Why? This is because causal models and the distribution change or distribution shift are heavily coupled. If you know X causes Y without common cause, you know that, oh, PX can change. PX can change, and the PY given X can change, right? They change independently. The 2 modules do not share information. This is known as modularity. The 2 modules do not share information. Similarly, if you observe the change in the distribution, right, you can verify whether they change independently. As a consequence, you can immediately discover information of the causal model. So right here, I'm reporting some basic results in this paper. And the conference versions of this paper were published 3 years ago. Right here, it's causal discovery from heterogeneous non-stationary data. So given such data, non-stationary data, what can we do? From the causal perspective, all those joint distribution changes, it might be possible that there are only very few causal modules that change over time across domains. That's good, because this way we can really have a very simple, have a very nice understanding of the underlying process. We can locate where the changes are, and we can further recover everything. Specifically, given non-stationary data over variables that V1, V2, V3, and V4, we want to do the following thing. First, you want to see for which variable mechanism changes, the causal mechanism changes. Yes, with the method, we can directly do that. We can see, oh, for those 3 variables, the conditional distribution given their parents change over time across domains. So their causal mechanisms change. And then we can find the right causal skeleton. And then by making use of independent change property or modularity property, we can find the causal direction. And finally, we can even find a way to visualize the change in the causal mechanism by discovering a low-dimensional representation of the conditional distribution across different domains or over time. I will just give some examples. Specifically here, I want to say something about the connection between independent change property and invariance, because a lot of people talk about invariance, right? So in this case, suppose we have VK and VL. In this case, VL does not change. The distribution is fixed over time. But the condition of VK given VL change over time. We said this is invariant cause, right? And in contrast, we may have invariant conditional given a VL given VK, but the marginal of the cause can change over time. So this is called the invariant mechanism. So you can think of the following examples. Suppose this is disease, this is disease, this is the symptoms. You can see across different regions, the probability, the high prior probability of disease may change dramatically, but the conditional distribution of symptoms given disease may be very stable, right? So this is invariant mechanism. You can also see examples for the invariant cause. Here, the point is that both of them are actually special cases of independent changing principle. Why? Because a constant is independent from everything. In this case, in the invariant cause case, this guy does not change. As a consequence, PVL, distribution of the cause, and the conditional distribution of the effect given the cause are independent, right? So they are just special cases. Independent of the condition is more general, and we can test for this condition to find the causal direction. Now you can see some results on the New York Stock Exchange market. Here we analyze about 90 stocks. We just analyze the daily returns. You can see the causal picture, and you can see companies in the same sector are usually clustered. You can see the asymmetry here, and right here, we just recover the driving force of the non-stationarity in the causal mechanism. This is 2007, this is 2008, financial crisis. We see that this curve is really similar to the so-called TED spread curve, which is the measure of the underlying risk in the market, calculated in a very complex way. So by analyzing only the daily returns, we can really recover the non-stationarity or change in the causal mechanism for a particular stock. We can even recover why and how it changes. Okay, finally, to summarize, we can discover causal information by making use of different levels of independence. You can use conditional independence, you can use independent noise in the functional causal model, and you can also use the independent changing principle. You can find causal information from data. It's not mysterious. So you can really discover causal information by analyzing pure statistical data. Now, let's have a look at the transfer learning or domain adaptation. Traditionally, we have training data and the test data. They are assumed to have the same distribution. That's why you can train something from here and then apply the learning machine to the test data. That's very good, classical thing. This is just a classical learning theory. However, in many cases in reality, we have source domains where you have x, y is the variable to be predicted, and then we have another domain where you want to make a prediction. And it's not surprising that the distribution can change because there are so many factors underlying the joint distribution of x, y, the feature and y. If the distribution changes, you cannot use the traditional learning method. You cannot learn something and apply the same thing to the domain. Instead, you have to do transfer. You have to transfer information from the source domain to a target. How can we do the transfer? Usually in machine learning, people just make some assumption, right? Assume this information does not change, then I can just leverage information from the source domains. That's not really a smart way to do so. Why? Because we have to really discover how the information changes, how the distribution changes. In other words, we have to find a high-level representation so that we have a bridge for different distributions. Because this bridge, we can jump from one domain to another domain. In other words, we can do transfer learning. Let me just quickly explain why causality seems to matter in prediction. Suppose this is me, right? This is my figure. This is my shadow. Consider two scenarios. First, suppose this is new scenario, new environment. First, suppose you just see my shadow. Can you say anything about my figure? I think a lot of you may say, yes, I know. I know you are here. I know the light. I even know something about the environment. The light is from here, right? And so on. Second scenario, if you just see me without seeing my shadow, do you have any idea about where my shadow is and how long my shadow is and so on? No, right? my shadow can be this short, can be this long, can be here, can be there, right? You have no idea. So basically, the causal direction is going from my figure to my shadow. This is because predicting cause from effect is generally easier. Why? Because the effect already contains the information of the cause. This is generating process. The effect already contains information from the cause, and also something from the environment. You just need to learn some constraints from your experience so that you can perfectly separate the contribution from the cause and the contribution from the environment. Then you can recover information of the cause, right? So predicting cause from effect is relatively easy if the environment is non-stationary. So in light of this, we have a couple of models for causal discovery. Y is the cause, Y is the variable to be predicted is a class level or regression target. So we want to predict Y from X. So in many cases, in this example, the digit you want to write down is the cause of the digit you actually wrote down, right? And disease is the cause of symptoms. So we have those causal models. We can have different ways to change the joint distribution. In all those situations, we can do adaptation. However, more generally speaking, we are given only data. How can we, if we are given only data, how can we directly leverage the data to find out what information to transfer? In other words, how can we discover and leverage the changeability, the property of changes of the joint distribution, especially in complex scenarios? So now I'm going to say something about this end-to-end method for transfer learning. First of all, I want to distinguish between causality and transferability. By causality, I mean we care about whether X causes Y, or we have a causal picture. In many cases, we just want to do prediction across different scenarios. We want to transfer information, right? So first of all, yes, causality helps for transfer. But we know that from data, it's really hard to discover causal information. You have to make a number of assumptions. But if you really want to make a prediction, you don't really care about the causality. You just care about the property of the joint distribution. Think about this example, classical conditioning by Pavlov. The dog can make perfect prediction by making use of stable association of information, right? So if a particular stimulus in the dog's surroundings was present when the dog was given food, then the stimulus would become associated with food and cause salivation on its own. The dog can make use of this association and make very good prediction and perform basically salivation, right? So we can do the same thing. We just make use of distribution, and we can discover very specific properties of data, and then we can make very good prediction. So right now, this is the idea from this paper, also accepted. Domain adaptation as a problem of inference on graphical models. How can we solve the problem? We are given data. From data, we just want to find the compact representation of the properties of the change in the distribution, represented by some graphical model, augmented graphical model. If you have a theta here, it just means the conditional distribution of this variable given parents may change across domains. Without that, we know our distribution is fixed across domains. So this is a way to represent invariant modules and change modules, and the changes are independent. And this is learned by the method for causal discovery from non-stationary data I just described. And then after that, domain adaptation is nothing but inference, Bayesian inference on the graphical model, given the values of those features in the target domain. Now you can find the posterior of the variable Y in the target domain. It's done. It's a standard problem, right? You can leverage a lot of tools to solve the problem. And from this view, domain adaptation is nothing but learning how the distribution changes, and then based on how distribution changes, you infer the posterior of the variable, target variable. And then this learned augmented graph can be very different from a causal graph, because right here, we only care about the properties of the changes in the joint distribution. It's not necessary to be causal. For instance, here, suppose Y causes X, disease, symptoms, and S is selection bias. So you just assign patients to different clinics based on the symptoms. This is the causal process. But if you let the data generated by this process, you will have this augmented graph. X causes Y. Why? This is because probability distribution of X right here changes, but the condition of X and Y does not change. So we do not have a theta variable into this guy, right? This is the compact representation of the changes of the distribution across different clinics. This is enough for our purpose. We only want to make a prediction in this changing environment. Although the direction is different from the causal picture, doesn't matter. Finally, here you can see some results on simulated data and real data. This is accuracy for prediction in the target domain. So you can see the improvement is really significant right here. It goes from 70 something to 80 something, from 60 something to 80 something, and from 70 something to 90 something, right? And on real data, you can see this is a huge difference for domain adaptation on Wi-Fi data. The performance was improved from 40 something to 70 something, and from 30 something or 40 something to 80 something. So you can really see a big difference. What that means? That means that by automatically discover and make use of the data, you can really do a very good job in transfer learning. Just let the data speak for themselves. To summarize, in this talk, you saw that how we can discover causal information by making use of different types of independence. With conditional independence, we have a constraint-based method. With the independent noise condition in functional causal models, we can find the causal asymmetry, causal direction between two variables. And as a consequence, we can find the whole causal DAG, causal directed cyclic graph, underlying the data. And in non-stationary environment, or with data with changing distributions, we can further make use of independent changing property implied by the causal module. And this way, we can find the causal information even in a very simple way. And finally, even if you want to do machine learning, including transfer learning, adversarial attacks, or dealing with adversarial attacks, and general purpose artificial intelligence, you have to go to the process or go to the information behind the data. So causality seems to provide a very natural way to describe the process behind the data. So if you go to the causal picture or something like a causal picture, you can really see the connection between different scenarios. You can really deal with the problems the current machine learning systems have. And as a consequence, you can achieve intelligence in a better way. Okay, thank you very much for your attention. That's all. Thanks. It's a bit longer.
Okay, thank you. Thank you for Dr. Zhang for the it's wonderful. It's really wonderful lecture about the causal discovery method. It is very interesting to know that causal discovery can reveal a lot of knowledge that we cannot do that before. And so now we are going to start the question and answer session. Is there any question already? You want to ask directly, probably?
I can see some messages in the chat window, so probably someone can take care of that.
Okay, so first is from
Rita.
Yeah, from Fahmin Rahim. The question is, in causal representation, I have heard that about the counterfactual model we're looking for the opposite output of factual data. Is it possible to do counterfactual research in the long term, like field in archaeology? Or maybe you can answer that first.
Oh, yeah, which one? The counterfactual one? Oh, yes.
Yeah.
So, yes, in scope of causal modeling, always about counterfactual inference. It's such possible to implement a kind of counterfactual inference. Oh, very good one. This is a very good one. So essentially, first of all, what is the counterfactual inference? You want, basically, let me just give the definition. You observe some phenomenon, right? Say today it's not raining, and then I see some phenomenon. Then you want to answer the following question: what if, what would happen to that particular thing if it had rained today, right? So imagine something different had happened, and then what would happen to a particular problem? Now, first of all, you're totally right. Without the causal picture, without the causality, we cannot answer such a question, because different causal road with different counterfactual result, which give different answers to the counterfactual question. Second, if you have the causal information, then you know what information you can make use of to answer the counterfactual question. What information is basically invariant information about the particular subject or particular unit. Suppose you are talking about me, right? Now, today it's not raining and I'm happy. Now you talk about the same person. You say, if it had rained, what would happen to me, right? That's the question. So right here, you want to make use of the hidden features about me. And when you answer this question, this hidden feature will not change. Now, if you understand this, you can see, oh, it's definitely possible to implement this procedure in a pure machine learning way, as long as you are given the causal picture. So the answer is yes. And then how can we solve the problem? How can we do so? You can just have a look at the twin world graph. Let me write down. With this graphical representation, you can really see the connection between what you observe and the counterfactual world. By leveraging this graph, you can easily apply some machine learning tools to give an answer to the counterfactual question, because this graph tells you what kind of information is changed and what kind of information is the same across the two worlds, the actual world and the counterfactual world. Okay, is that answer to your question? So currently there's no such a method. There's no implementation to do this, but you can develop one, and it's possible. And the basic idea is to make use of this twin world graphical representation of counterfactuals. Uriel, is that answer to your question?
Yeah, probably. And this is also a question about the counterfactual inference also from Uriel Wijayanto. He also gave a question on chat. So he also passionate about the counter inference. So he asking about.
Yeah, I answered that question actually.
Okay, yeah. So
yeah, I answered. But there's another one, right? Before that.
Oh yeah. Oh yeah.
Okay, let me.
I thought you.
Yeah, let me quickly.
Okay.
Oh, sorry. That's a counterfactual one, because you mentioned that one. I started with that one. So
okay.
The question before that is in causal representation. I have heard about the counterfactual or model. Oh, it's also about the counterfactual. Sorry, that's why.
Yeah, that's also.
When looking for the for the opposite output of factual data, is it possible to do counterfactual research in the long-term like field of archaeology? I would say you have to think about what you mean by counterfactual research. It's a standard term, and there are kind of standard techniques. So in some fields, counterfactual is not, people do not really understand the counterfactual questions. So you may introduce counterfactual questions and make it very clear what problems you can solve by using counterfactual questions, right? And I would say in a number of fields, including healthcare, in anomaly detection, counterfactual questions are very, very important, and people should pay more attention to them. So in those fields, definitely you are totally right. In archaeology, probably you can do something similar. Basically, with the counterfactual questions, you want to have an individual understanding of the problem, right? Because you really want to see the cause of this particular phenomenon, or you want to change, you want to make a change such that this particular problem will be solved. As long as you have such questions, you can do it. Okay. Is that the answer to your question, Fahmi? Okay, great.
Yeah. You also give a message in chat already. So there's another one also about the high dimensional data. So what is the best feature selection approach to use before we fit our data to a causal discovery algorithm? Maybe.
Very good one. This is very Okay.
Yeah,
very good one. Very practical issue. Yeah. There's some delay. Sorry about that. So first of all, there are some causal methods for feature selection. So you know, in PC algorithm, right? We need to find the skeleton, and the first stage is to discover the skeleton, and a method called FAS. It's fast adjacency search. Aimed to do so. You can just find all those variables adjacent to a particular target variable, right? So I would say, if you want to really solve the problem, you can start with, let me write down. Any reliable method for Markov blanket discovery, because the Markov blanket contains all the variables that are possibly the causes, parents, and the children and the spouses of this variable, right? So with this kind of information, you can really reduce the space of the hypothesis model. You know, a lot of links cannot be there at all. So we have the method called the two-step method, published last year in Network Neuroscience, two-step method. Essentially, this method makes use of Markov blanket, and Markov blanket is a way to do feature selection, right? And of course, you in very complex situations, say nonlinear situations, you can use other methods for Markov blanket discovery. In that method, we assume it's linear. That's why we use a linear method. We use graph lasso for feature selection. You can even use deep learning tools to select the features, as long as if the relations are nonlinear, you can just use a lot of packages to select variables, relevant variables. Essentially, my recommendation is that you learn the Markov blanket, you start with the Markov blanket, and then the problem will become much simpler, and you can solve the problem in a much easier way. Okay. Is that answer to your question, Fajar?
Is it clear? Oh yeah. Yes.
Okay.
I think yes.
Great.
So is there any more questions, please? So probably this is my my experience. So I want to ask about the if we use DAG, Dr. Zhang. So we have a if we get a direct causal effect, so we have an arrow there. But how we explain about the undirected edge? So how does it?
Okay,
work?
that's very.
Yeah.
Oh, a very good one. So let me just go to that slide. First, here I have 2 points to make. First, in many cases we have cycles. In many cases we have cycles, right? And actually, there are so many methods to deal with cycles. Of course, I don't have time to talk about that. But last year we had a paper in Network Neuroscience comparing different methods for discovering cyclic graphs. Cycles are almost everywhere because of feedback, right? The system is stable. That's why. So if you want to see how to discover cyclic models and how to understand this cyclic causal representation of the underlying process, please refer to that paper. And then let me just focus on how to interpret the undirected edge right here. So this is our output of PC. You can see some edges are directed and some are not. Basically, this is called a pattern. because with conditional independent based method, we can only end up with a so-called Markov equivalence class. All decks here in this class, this is the class, all decks here have the same independence and conditional independent relations. And specifically, first of all, we can show that all decks share the same skeleton. That's why we can use this as a representation. Second, if all decks in the solution class have the same direction for this edge, then this edge will be directed. So this just means, oh, I can determine the causal direction here. And for some edges, the direction can go in different ways across different solutions. And then we can just give undirected edge. This just means, oh, this guy can go here or here. However, let me give a simple example. Suppose we have three variables, and suppose this is the true model, x1 cos x2 cos x3. From this true model, or from data generated by this model, suppose you have enough data, then you can see x2, given x2, x1, and x3 are conditionally independent. Given x2, x1, x3 are conditionally independent. Now, unfortunately, given this, first of all, we know they are not adjacent. It's good. So we have a skeleton. On the left, you can see this is a skeleton. And you want to go further to different direction. But unfortunately, right here, this is not a V structure. They are not causes of this common variable. You cannot determine the direction. Why? Because in this case, the three possible solutions will give the same conditional independent relation. The first one is the true one. Direction goes this way, from x1 to x2 and then to x3. It's the true model, right? This one will give this set of independent relations or conditional independent relations. And this guy will also give the same. x2 is the common cause for x1, x3. You have the same independent relation. x3 and x4 will be conditionally independent given x2. And similarly, the direction can go this way. x3 cos x2 cos x1. Even if this is the case, we still have the same set of independent relations. Meaning that in this case, with only conditional independent relations, we cannot distinguish between the three possible solutions. And you can see the three possible solutions have different directions for each edge. As a consequence, we have to use undirected edge in the final solution. And this solution is the class or set of decks is called a pattern. So if you are sure about the direction, yes, it's directed. Otherwise, you just use the undirected edge. If it's undirected, it just means that it can go this way, can go this way, or this way. However, we also know that the directions are not arbitrary. For instance, if you know that this guy goes this way, if you know this, just like the example I gave here, suppose we know that direction goes from location, geographical location to climate, then this guy must go this way because otherwise you are going to have a fake V structure.
Okay.
This is a possibility you can exclude in this case. Okay, so you can see how to interpret the result given by PC, which is a pattern. Is that answer to your question, Feri?
Yeah. Thank you. It's very clear.
Okay, thank you very much.
Yeah. So is there any more questions? No? Okay. I think there are. Oh, this is one more question, I think.
I heard terms that I think are similar. Yeah. Oh, this is a very good one.
Yeah.
Causality, explainability, and interpretability of machine learning interchangeable words or refer to the same meaning. Oh, this is a very good one. I would say the picture is very large, very big. It's hard to say. First of all, they are not interchangeable. They are not the same thing. Why? Because you can achieve interpretability by making use of a lot of a lot of other kind of information. For instance, some people try to achieve interpretability by enforcing the decision process to follow some structure, the decision tree, right? In the deep learning, I force some part of deep learning to follow the decision tree structure. And then I say, I believe decision tree is interpretable because I know how to make a decision. I care about this feature first, and then I make use of another feature, and then I make my final decision, right? So you know the decision process given by this particular method. If you just leverage that, you can still achieve interpretability. So the point is, it really depends on how you understand interpretability and explainability. From my perspective, I agree. We have to go to the causal level to give the very natural interpretability. When we want to explain why we make this decision, we just want to give the causes of this decision, right? That means in deep learning, we really need to find a way to integrate or to automatically learn and encode the information in some way. If you can do so, then you can say, yeah, now I just consider interpretability as something that can be derived from causality. That's totally fine. But right now in machine learning, most people do not think so because most people are not familiar with the causality, right? People have different ways to achieve interpretability and explainability. And you're right, because there's a gap, right, between different subfields. Is that answer to your question, Ryan?
Is that clear, Ryan? Yeah, I think it's clear now. But probably one more questions, and we will close the
Great.
question.
Okay, this one
answer.
to save time. Yeah. What do you think are the areas of research that we can apply your topic, especially in the time of pandemics? Very good one. We are doing a project right now, so it's really essential to discover the causes of the spread of virus. In particular, in this picture, from the causal perspective, from the machine learning perspective, right? If you just want to make prediction, you just go from, say, infection data, right, to make prediction into the future. Or you want to see how the infections are propagated in some regions. But from the causal perspective, if you really want to understand what's going on, we have to pay attention to the following things. First, how different policies, right? How are the policies effective? Second, are there a lot of causal influences non-stationary? I believe so, right? And third, how can we really discover almost all possible causes of the spread of virus? And fourth, very importantly, we have to distinguish between the underlying infections from the measured data. You can, if you just look at data across different countries, you can see different countries have very different capacities of testing, right? As a consequence, you cannot really trust their the reported data. You have to separate the measuring process from the causal process. The causal process to produce infections, and the measuring process to produce the reported data from the actual infections. If you can achieve those 4 points, I would say this research is wonderful, because you can give suggestions regarding how to prevent the spread, and also you can give suggestions as to how to correct the data, right? And you can also make prediction into the future, because you know how different relations or different influences will change as time goes on, and so on. So if you want to discuss more detail, maybe you can just email me afterwards. This is a very good question. There are so many things to be done in this particular topic from the causal perspective, from the rigorous causal perspective. Okay, great. Thank you.
Yeah, thank you. So yeah, we have to stop now because we have another agenda after this, another keynote speech. So thank you, Dr. Yang. It was a wonderful lecture. It is our pleasure to have you here this moment in this session. Yeah, even though it's just online. So we hope that you can visit us in Yogyakarta somewhere in the future.
Thank you. Okay, thank you very much. Thanks for the organizers. I also thanks to Rito who is here. It's really wonderful. I hope I am looking forward to the great success of the conference. So everyone, please have a good time. Yeah, thank you very much.
Yeah, thank you. So yeah, thank you for all of you who have been joining us for this session. Yeah, this is the end of this session, this lecture keynote speech session, but this is not the end of the conference. So please enjoy the next agenda of this conference. Thank you.